The term noise has many different meanings in various disciplines and quarters. And so we have to define here what we mean. Here it is meant as internally generated variability which cannot be traced to external drivers. That is, so to speak, smoke without fire. And we conceptualize it as stochastic variability, possibly conditioned by some state variables. And I claim that noise is an ubiquitous constitutive element in the dynamics of climate. Now, just a very simple example of how to generate noise. On the top right diagram, you see time series generated with a very simple nonlinear system, actually two realizations. And if you add 100 or so of them, then normalize it, then you get in the middle diagram one of the two curves. The second curve, I'm not sure which one, is just generated with a random number generator. Of course, the random number generator is such a strange nonlinear deterministic thing, but practically it is pretty good to conceptualize it as noise. And if you look at the distribution from these many nonlinear components, then that's the lower diagram. We see that we have something like a bell curve. So the mathematical construct of randomness is an adequate concept for the description of features resulting from the presence of many chaotic processes. In the old questions of physicists, is God rolling a dice is irrelevant, because as long as we cannot discriminate if he does or does not, it doesn't matter. We just treat it as if. No? Okay. Now let's have a first example. This is from a paper which we got out in earlier this year, and it shows temperature at some location, doesn't matter which one. And we used a regional atmospheric model covering Northern Europe, something with a resolution of 20 kilometers or something of that sort. And so it was driven with observed data or analyzed data at the boundaries. We generated two ensembles of extended simulations, and we used always the same regional atmospheric model. One ensemble of 5 members was generated by using different times to begin the calculation, but they all cover the year 2000, was it 18 or 19, and it was exposed to the same forcing, only that in one case it was begun on the 1st of October a year before, and the other one on the 1st of June or anything of that sort of that year. But we evaluate 2019, and so the 2019 in both cases, in all cases, is the same. And what we get is the top right diagram where you see the temperature development, and you see there's some mumbling in the beginning, then it falls almost quiet, and then the variability starts in you. And there's no system in these variations, it seems. The second ensemble is done in a very similar way, but they all use the same initial time, the same computer, the same forcing, everything is the same, but it is run on a different computer. That's all. And so that's a middle diagram, and you can see that essentially we get the same result. And to compare these, we have in the lower diagram the standard deviation for each of the days. I mean, this is given the days here. Yeah. For the two ensembles, and you see that the standard deviations of these curves is really very similar. So we have here simulations which show episodes of what I call intermittent divergence in phase space, and that's the key point, at the same time in all members of both ensembles. And indeed, these episodes coincide with boundary conditions which impose a weak through flow. It means provide dynamical conditions allowing for the minuscule noise, for instance, by using a different computer, to manifest in large scales. Okay, this was one example, and here we have a different type of thing. This is on the left, satellite image from the Baltic Sea, and you see on the right-hand side, this is Saaremaa in Estonia, and here you have Gotland and Sweden, and you see all these cyanobacteria, which indicate the turbulent, macroturbulent character. See all these things in the Baltic Sea. And here we have an early analysis of high-frequency variability, small-scale variability, also in the Gotland Basin. And you see this in similar, this very noisy behavior. Now, to demonstrate that this is really working in action, is we have a public relations activity at our lab, namely that we visit with our little research vessel German ports in summer for a week and invite people to come on board, have open ship, and we asked students, pupils, to write letters, which will be sent out as drifting bottles. And you see on the top left diagram, you see the drifting bottles. And then on the lower left, you see our captain setting these bottles out. And they were set out on the 15th of July, 2019 at this star, at the same time, at the same location. I mean, of course, something like 15 meters apart or so in 1 minute. But the interesting point is, where were these found? And these are the locations where they were found are given by the orange points. So 2 are in the left, in Trelleborg, and on Rügen, but another 5 or so were found in the northeast, in Gotland and Öland. So obviously there's something high frequency variability going on. And so we simulated this with a transport model where we had a random displacement at every time step, a very small displacement. And in this way, we got 2 very different trajectories we calculated a lot. Starting here at this red point, and in one trajectory, the bottle within 90 days would travel this way, and in another, it would go this way. So sometimes to the northeast, and sometimes to the west. And I will not explain this on the right-hand side to save some time now. Now, we can think, of course, what are the reasons for this? It could be wind drift, inertial oscillation seaches, and various other things, in particular Gaussian coherent structures. And an example is shown on the right-hand side. This is the Gulf of Finland. That is the water body between Finland and Estonia. And on the right-hand side of these diagrams, you would get St. Petersburg every while. So in the beginning, Valley, who published this, had uniformly distributed particles in this sea. And then he started his integration with a very high resolution. And then after 5 days, for instance, you get this very well structured thing here. I mean, this is all small scale, and the best way to understand it is to say, first of all, it is noise. There's no specific reason why it looks like this. Well, it depends on what you call looks like. I mean, is anybody responsible that this is here and not here? And I would say no. An old example is when we had a simulation with a coupled atmosphere ocean general circulation model for 1,000 years. The model was subject to periodic forcing of solar radiation, the annual cycle, but otherwise no variable forcing is acting. So the weather is made by itself. We had no CO2 increase, no volcanoes, no variable solar activity. And here on the top right side, we have the temperature, the mean air temperature for Europe. And you see that there's quite a substantial variability in the system. And we have sometimes here, this is something of the order of 50 years or so, a deviation of 0.5 degree. So also here, we cannot say why this is happening just here, but it's part of the internal variability. Now, let's go now to how all this came about. And I would say a key person doing so was Klaus Hasselmann, who published 1976 his paper on the stochastic climate model, part 1 theory. And this is a diagram of him just a few months ago. So he's obviously is quite happy with life, at least at that time. And I mean, to put it very simple, the stochastic climate model I'll summarize it here, but this may be even too strong a simplification. Before introducing this concept, and again more and more so in recent times, people were convinced that all remarkable developments in climate must be related to one or more external reagents. If there's fire, if there's smoke, there must be a fire. But Klaus demonstrated there's smoke without fire in climate variability. That is, low frequency variability is generated as the integrated response to short-term fluctuations, for instance, macroturbulent atmospheric flow at mid-latitudes. Thus, a new task of climate analysis emerged, namely the question if an anomaly is just part of the internally generated low frequency variability or caused by specific external causes. That's the concept of detection attribution. And I mean, very simple, what he's saying is, let's consider that we have a system governed by the differential equation given with the star here. And so we have state variables x and forcing F and dynamics D. And now we assume that x is made up of two components, y and z, which fluctuate along in short-term scales. And after linearization, we find for the slow component for y, the time derivative of y is d times y plus w, and w in independent short-term variability. And d must be less than 0 to have x stationary. And after we have discretized the whole thing, then we arrive at an autoregressive process of first order, which has a red spectrum, even though W has a white spectrum. Now, thus, these models of the dynamics components of the climate system generate variability on all time scales without being provoked for doing so. We have smoke without fire. Now, what does it mean? And part one deals with the issue of noise as a concealing element. And the presence of noise hampers the identification of forced changes in the models and in the climate system. And one point is, if we interpret numerical experiments with dynamical models, then this is the point, and I have an example to show here. And when we try to identify the effect of anthropogenic influences on regional climate, then the detection attribution issue comes up, and you have another example. So to start with, here I have 500 millibar hectopascal maps from times nobody of you remembers, a part of elderly gentlemen like Antonio Navarra and myself, and it shows just they are different. And we have no reason to think that there's any reason why they are different. They're just different. On the other hand, we have here the temperature development, the famous curve, which is at the base of our concern about climate change. And we see here variations, but we see also a trend, an upward trend. The question is this also just noise? And I will show, and we know now by now that it is not. So to deal with that, we use statistical tests of a null hypothesis. And this is a suitable tool for discriminating signal, that is, a change due to external causes from noise, which is variability internal to the system. By the way, this was the first paper I'm aware of this. It was done by Chervin, Gates, and Schneider in 1974. And the null hypothesis is that an observed change delta is related only to internal variability. And the alternative hypothesis is that at least part of the observed change is caused by external factors. And to discriminate these two options, a random variable S is built, which describes the outcome of the sampling process if the null hypothesis is valid. Now, if delta is larger than a critical value, the pth quantile of S, given the null hypothesis, with a subjectively chosen P, then the occurrence of delta in a regime given by the null hypothesis is sufficiently rare so that we conclude that the null hypothesis is false, and the alternative hypothesis accepted as valid. Now, statistical tests are asymmetric. Their outcome is either the rejection of the null or the non-rejection of the null. The former is taken as evidence for accepting the alternative as true. The latter represents insufficient evidence for the alternative, which is not to be taken as alternative is false. And here I have an example. This was an experiment which was done with a coupled regional atmosphere ocean waves model, ECAVM. And the region is shown here. You see the North Atlantic. And two ensembles of simulations were generated. A control one where the sea surface roughness is obtained from the standard Charnock relation. And then a second ensemble where the impact of wave is explicitly accounted for in the sea surface roughness using wind over waves coupling theory. And what comes out is that we have, this is air pressure, by the way, we have relatively large differences in air pressure, that is the isolines. But if we do our local t-tests, then we find that these relatively big changes are not significant. They cannot be discriminated from noise, given the setup, while we have significant changes everywhere here, where we actually have very small changes. That means here we have significant differences which are physically irrelevant, while here we have differences which are statistically not identifiable. Second part is detecting externally caused climate change and attributing plausible causes. So we have looked at South America. So this is South America here, Brazil. And here we are looking at precipitation trends in August, in the period August to October over 1983 to 2012. And we find in these blue areas that the change is beyond the range of natural variations. So the null hypothesis that is, it is natural due to internal variability can be rejected at the 5% level. So we have detected something. But now comes what do we use as explanation for that? And this is the so-called attribution challenge. We determine a mix of plausible external forcing mechanisms that best explains the detected variations. And the attribution is the result of a plausibility argument. It identifies a set of possible causes which efficiently describe a cause, which was earlier detected as inconsistent with internal variability alone. Of course, it could be that there are other explanations as well, but we are not aware of them. Now, in the case of tropical South America rainfall in fall, we have looked at the influence of greenhouse gases and land use. And we have, in this diagram, but I do not have enough time to explain that in any detail here, we see that we would expect that the greenhouse gas signal should have a signature in this area here and the land use here, while if there would be only natural variability, then this ellipse would be centered on the zero. But indeed, the zero line here and the zero line here are not covered by this ellipse, spanned by the two bars here, which means the explanation by simultaneous influence of greenhouse gases and land use is more efficient at explaining the difference than the earlier rejected natural variability. Now, the part one, the conclusion here is noise, understood as internally generated variability, which cannot be traced to external drivers. It is conceptualized as stochastic variability, possibly conditioned by some state variables. Now, noise is ubiquitous in the climate system on all scales due to myriads of nonlinear mechanisms. And it is not relevant if this variability is real stochasticity or if it's just impossible to discriminate the variability from stochasticity. Real stochasticity is the most useful mathematical construct. It doesn't matter if it is real or not for our process of understanding. Now, the presence of noise changes the dynamics of the system. The mean circulation would be different if there were no storms. The storms were different if there were no convective cells and so forth. And for the practice, it's important that noise hinders the identification of externally forced signals, and the utility forecast, by the way, and the attribution of anomalies to specific causes. Now, part two. Hydrodynamic noise in high-resolution marginal sea models. the quotation mark high resolution should be closed here, because what today is high is low in 10 years' time. And this is based on a number of publications which I have prepared with my Chinese students in the last years. So the first one is we use the model HIMOC. It's a hybrid coordinate ocean model, a primitive ocean model into 3 vertical layers. And we have done multi-decadal simulations. And first, almost global one with 1 grid resolution that is shown by this diagram as a whole, then nested into it one way. If we turn off my telephone here. So, then embedded into that is the first red box, that's the West Pacific WP model with 0.2 grid resolution, and the South China Sea model, that's a smaller red rectangle with 0.04 degrees grid resolution. The first model hardly describes macro turbulent eddy dynamics, but the other 2 models become better and better in doing so. And so keep in mind, in this set of experiments, we have prescribed atmospheric forcing without weather. We only have monthly means, and it is strictly annually periodic. So we have no day-to-day variability. So we show here the spatial distribution of the mean intra-seasonal variance of sea surface height in the South China Sea in summer. And we have here the 3 models: the global model with 1 degree grid resolution, the West Pacific model with 0.2, and the South China Sea model with 0.04. And you see that the variability becomes bigger and bigger if we go to higher resolution. This comes from, obviously, because we have more higher resolution in space. And a significant contribution of this noise comes from the generation of eddies. In the 1 degree simulation, hardly any eddies are formed. In the 0.2, quite a few, but much more in the 0.04 simulation that is shown by the 2 diagrams on the top right. It's only showing the eddies in the area where the depth is 200 meters or more. And we have, on the lower diagram, we have the number of eddies in the West Pacific model, 0.2 degrees. That is in, not sure how to call that color. The red bars are in the South China Sea model, and we see we have variations. So it happens, it goes up and down. In these there are no specific reasons. We could not find reasons why that would be so. And but it's much higher than in the 0.2 degree. Since the atmospheric forcing is constant on monthly timescales, and all atmospheric variability comes from a constant annual cycle, the formation of eddies represents the generation of intrinsic noise. The second model, we had actually weather variations, realistic ones, and we have now an ensemble of 4 simulations, all covering 2008, and we use the boundary and initial values from the previous West Pacific simulations. And so we had different starting times. So it's December 2007, October 2007, December 2006, and October 2006. But they were run through all of 2008, and the atmospheric forcing was in all simulations the same. The paper came out in JPL. And so we have as noise, we define the annual mean of the daily standard deviation in the 4 simulations at the same time. And as signal, we define the annual intensity of the coherent variations of the 4 simulations. That means the mean stuff. We are looking at the daily fields of barotropic stream function. We could use others as well. And we expand it into empirical orthogonal functions. Now, we can assign to the EOFs by using spatial statistics a spatial scale. And the result of this effort is shown in this diagram. It shows the spatial scale length versus the number of the EOFs. And you see the low indexed EOFs have large scales. I mean, that's what you would expect. And the high indexed ones have very small scales. So we can say the EOFs are ranked by scale. And so if we go now for the signal to noise ratio for EOFs, we have three range of spatial scales. The first one here, we have a spatial scale of about 220 kilometers. That's this red thing here, this part here. And if we just look at the local signal to noise ratios only for which are spanned by these first few EOFs, and we see there's still quite some structure. Sometimes the signal to noise ratio is large, in particular along the coast. If we go to the middle domain here, this here, it has a scale of 110 kilometers. We have almost uniform signal to noise ratio, low ones. And if we go for the tail of this distribution, where we have a scale of 30 kilometers or so, then we have just uniform, almost uniform conditions. So the noise is essentially going on, of course, on the small scale. And the last experiment is we were asking, when discussing this with regional oceanographers, some of them told us, well, you can't forget about it as soon as you turn on the tides, because the tides were destroyed. And this argument is partly right. So what we did here is we're now going to the Yellow Sea and the Bohai. So you see here, this is Korea here, South Korea, North Korea, in China, with Beijing about here, and Qingdao about here. So this is the Bohai, this is the Yellow Sea. And again, we have 4 simulations starting in September 17, January 2018, March 2018, September 2018. And we evaluate the 2019, the joint period. And we determined again, we determined again the signal to noise ratios for, yeah, unfortunately, I cannot really see that here. Anyway, the signal to noise ratios for temperature, barotropic velocity, and salinity as a function of EOF in the control with tide simulations. And we can see here that for the black part, that's the velocity, the signal to noise ratios show very similar behavior as we've seen before. The temperature also, but the salinity, we have all very small signal to noise ratios. And again, here is the signal to noise ratio for medium spatial scales in the control simulations. We see we have some signal, some coherent variations in the 4 simulations in the coastal regions, but not in the inner part of both the Yellow Sea and the Bohai. And now, what happens if we turn off the tides? And then we see, for instance, here, which is, forgot which variable it is. We see here the signal to noise ratios if we have the tides on, and in red if we have them not on. So the tides contribute strongly to the signal. And if we go here for the 3 EOF ranges, if we have noise turned on, then the noise level here is yeah, the noise level is about 1 times 10 to the minus 3, and without it is 1.3. So it is the noise is larger, but the signal is also larger. But if we go to smaller scales, then we have almost the same. The noise width is reduced. Yeah, if we have the tides on, these numbers are smaller than here. These are smaller, and they're about the same. And that means the tides are actually contributing to the signal. Now let's conclude that the second part. The noise is dynamically consistent with the local hydrodynamic environment. But noise is not space-time uncorrelated scatter. It is not white. In marginal seas, it's mostly a small scale, less than 200 kilometers. But this is also the area where lots of the applications, the impacts are taking place in terms of river discharge, in terms of ecosystems. It can be made up of mesoscale eddies, but also by other small-scale dynamical features. And multi-year climatologies of eddy statistics are hardly available and need to be constructed mostly by dynamical models, validated using recent satellite products. We've done so for the South China Sea, but there was very little otherwise. And interestingly, we could not build empirical models, statistical relationships between properties of, say, the number of eddies or the intensity, the mean intensity of eddies in any large-scale features. So we couldn't do anything like downscaling. Now, the overall conclusion, and this brings me to the end of all this. Noise is not an inconsequential addition to the overall variability of the climate system. It modifies the variability on all scales. That is Hasselmann's stochastic climate model. It affects the local environment of impact. So on scales where lots of ecology is going on, where lots of morphology is going on, things have an extra dimension of variability. And it makes efforts needed for discriminating noise in the signal in observations and in numerical